All right, so now we're actually going to start the Regression Roadshow. We're going to be going through a large number of different regression model approaches, very briefly covering some of the pros and cons of each. In class, we're going to go into a little bit more depth on each of these models and how they work, but still not a lot. This is really a breadth-based approach to teach you about the tools that are available to you. First, we're going to just go through and fit these models and describe them. Later on in the lab, we're actually going to then look at how we can compare the accuracy of those models. So the first thing that we need to do is that we need to actually get our data frame into a format that works with the modules that we're going to be using for the models. So the models themselves are all in something called scikit-learn, sklearn, and that sklearn requires things that are a little tiny bit different from pandas. So first, let's go ahead and define what we're going to predict. So we're going to be predicting the number of persons. And so what this line is going to do is going to define a new variable y that is equal to just the person count. We are, the pop actually removes person count from DTA clean as well. So it will no longer exist. So if we type in DTA clean.columns, run this, you'll see person count is no longer in this set of columns as we would want. Additionally, you'll see if we run this again, it can't work because y can no longer be set to person count because person count no longer exists in DTA clean. So I'm going to go ahead and run this again up here, this DTA clean. I'm actually going to take this and copy it down here so that we can now run this because I'm redefining DTA clean. So now this will work every time. Okay, so x we're going to set to what's left of DTA clean. You'll remember we removed person count, so now we can just say x is everything else. So x is going to be CNN 1, 10, 11, 12, 2, 3, 4, so on and so forth, and image brightness and minute. So we're going to be using all of that information to predict person count. Now, one important thing that we have to do is actually scale all of our data. We've talked about this before, making sure that everything is on the same kind of set of dimensions so that, minute, because it's measured in minutes, is comparable to the image brightness, which is measured on a scale from 1 to 255. So we're going to use the pre-processing routines that we've used before. And it's going to be a scaling model. So what we're doing here is we are saying, let's create a new scalar, something that is going to scale our data. We're going to use a standard scalar in this case, and we're going to do it based on all of the data in X. So then we'll do X scaled. Here's where we're actually applying that scalar model. So this is what will actually give us our new variables, which are the scaled versions of X. We can see what happened here. So let's just do a quick little look. So let's take, this is observation 996. You'll remember there were 2,800 minutes. This is the 996th minute in what we actually got. So if I run this, you'll see this is the original data in the in our data frame. So image brightness is a 14, minute is 996. These are very, very different scales. If we now look at the after scaling, so I'm going to just add this in as well. So this is the exact same thing, except here I'm doing X scaled 996. Here I just did X. And you can see here, this is actually the scaled versions of the exact same variables. So this 0.51, this became a negative 1.63. The reason this 0.5 became a negative 1.63, what this means is that for row 996, the value for CNN1, 0.5, is less than the average across all of the units of observation. We can also do things like this. So because we've defined our scaling model here, so this is where we've actually said this is how our scaling model is going to work. Let's say that we only wanted to scale the model, these values, only the values from 996. This is how we would do that. We would go in, we say, okay, for that scaling model, transform only the values in row 996, and we have to do this .values.reshape for the transform. This is just something that's necessary. In the example case, we would then have to actually apply that particular transform. So this is saving this into an X example case. So if we run this, we can see here, this is the same thing, right? There's no difference here. except what we've done is we've output only the one row of data. And we'll use this X example, so this one row of data, we'll use this a little bit later on. So we're going to save this for later use. The first regression type that we're going to test is something called lasso regression. So lasso regression, it's something called an L1 regularizer using mean absolute error. Again, we'll talk about more of this in class. But the key thing here is that it can drive coefficients all the way to 0 and effectively remove things from your model. This can help you identify the variables that are the most important, because it's going to penalize you for including too many variables in your model, or having kind of large coefficients for some variables in your model. This is helpful if you don't know what's most important and you want to avoid overfitting. So to do this, we'll do from sklearn import. It's a linear model, so this is a class of linear model. And we'll go ahead and define the model itself. This is all it takes to actually fit this model. So this will provide us with a fit linear lasso model using all of the CNN data that we had before. Now, let's say that we actually want to see the estimates that this particular model will give us. So you'll remember that the way that these models work is effectively we are saying that y, so in this case the number of people that we are estimating are walking in front of the camera, this is equal to some set of parameters times each other and plus each other. So beta 0 plus beta 1 times x1, where x1 is this value here. So some number times 0.5 plus some number times 13.4 plus some number times 2.97 plus some number times 14.6, right? We're trying to figure out what are those sum numbers. That's the whole point of these exercises, to find the best set of numbers to multiply by these columns that give us the most accurate prediction of y possible. So if we want to actually see, we fit this model, let's see what those actual numbers are. Let's see what the numbers are that it's predicting. So to do that, this line of code right here, we're doing the zipping the coefficients. So this is the actual estimates they make to the names of the columns. So you could just do lasso model.coef, and this would give you the numbers. This tells you, this just puts the names of those variables beside them to make it easier to see. So let's run this. And you'll see, so these are those actual parameters that we are fitting. And this is with the lasso model. So let's take just an observation 996. So this is the 996th minute of the day, or of the 2 days. If we wanted to make an estimate of how many people walked by the camera on this minute, what we would do is we would first standardize these values. So you'll remember, this is the raw data. So CNN1 in the raw data is 0.5. This is the standardized value, so negative 1.6. The first thing we would do is we would multiply negative 1.6 times negative 0.18. We would then add that to negative 0.596, the second number. So this is, again, 996. This is the value it had for CNN10 after we standardized. So negative 0.596 times 36.41 plus CNN11, negative 0.23 times 34.78, so on and so forth for all of these coefficients. And when we add all of that up together, that's when we get the actual prediction for that row. So let's actually do that, and we can do that using scikit. So this is a much easier command to write. So this lasso model.predict. So again, we fit it here. Now we're going to use it for a prediction, and we're going to predict for the X example. So this will actually give us, you'll remember we created X example up here. This is the scaled value. So this is X example. This is exactly what X example looks like. And so we're going to do that multiplication here. So let's run this. And here we go. So this is the estimate for this particular row that we would get. So we're going to get 57.355. Now, let's just say, for the sake of, we're interested, what is the real value? We can also look, if we print out here, the y for the same minute. So minute 996. Let's run that. And here we go. So we see that the real answer is 104. So if we take the real answer of 104, this is what we know the number of people truly were, and then we compare that to what we're predicting, which is 57. So our prediction is under what we know to be true. But we're predicting using information that is this camera sensor information, so we don't expect to get it perfectly right. What we're curious about is which one of our approaches kind of gets the closest. So we know lasso is underestimating. If I'm going to add the print y here. So we'll print y here. So we have this true value of 104, and this is 57. The question is which one gets the closest. Now, we're only going to be looking at this one example, minute 996. Later on in the lab, we'll look at how we can compare across all of the different minutes and to see which one on average gets it best kind of across all of the minutes. So the second type of approach we're going to use is something called orthogonal matching pursuit. This is another way that you can penalize using too many variables. Essentially what it's going to do is it's going to find a starting model and then choose new variables to add based on what variables are most highly correlated with the remaining errors. And again, we'll cover these more in class. So from SK. Okay, so this is exactly the same as before. We have up here, lasso model equals linear model.lasso, random state 1693, and then we have the lasso model.fit x scaled y. All I've done is I've taken this and I've put it all in one line here. So we have the model being set, we have the orthogonal model matching pursuit dot fit, and the dot fit says just go ahead and immediately fit it. So this reduces that down. We're still using the x scaled and the y, so nothing here is changing. Capitalize the x. And then we'll go ahead and do the same print that we did before. So I'm going to print two different things. I'm going to print the coefficients that the orthogonal matching pursuit model predicts, and then I'm going to predict the example for just that one row, that row 996. So we'll run this. And so now that I've spelled everything correctly, you can see this is the exact same thing. So here we have CNN10 is the only thing that has anything. So to predict the total value for any given row, all we're going to do is multiply CNN10's parameter by the value. So if we do that for this x, so CNN10 for x, we have 13.49 here. We have negative 0.596 here. If we go through and we do the multiplications, we actually get this value, right? So this prediction from the orthogonal matching pursuit model of 77.67. This is going to be slightly different than the obvious answer just because there's going to be some, all of this might be 0.0, but there's actually a very, very, very small value somewhere out here. So this is better, right? The orthogonal matching pursuit model is overall giving us a slightly better estimate than the kind of lasso model did. So let's go to the next one. This time we're just going to do a very, very simple linear regression. So linear regression, this is kind of, the thing that you would learn in any intro statistics course. Okay, so again, the exact same thing. Now we have all of these coefficients. This is a different set of estimated coefficients. You'll see some broad trends. For example, the coefficient on CNN10 here is the highest of all of the, I believe, the highest, yep, of all of them. Here it's the only one. Here it's also the highest, I believe. Yep. So the fact that CNN10 is always coming up as the highest generally tends to indicate that CNN10, whatever this might be the number of vertical lines the camera sees. This is containing some meaningful information that is well correlated with Y. So all of these models are taking advantage of that. So this is for that one observation, again, what we would predict, the 59.74. You generally would not want to use linear regression. It's very, very common, but it's rarely the best model that you would want to use. It has kind of a lot of the negatives and few of the positives associated with other models. The biggest risk for linear regression is the risk of overfitting. That is, every single one of these variables is used to predict Y. If you look at orthogonal matching pursuit, only one variable is actually used, really by any meaningful measure. So here, this is not going to be as kind of likely to be overfit, whereas this one is very likely to be overfit because all of these different variables are being used extensively. So linear regression kind of has some pretty major drawbacks, and it's quick, but it's rare you would want to use it. The next thing that we're going to look at is ridge regression. We're going to talk more about the difference between ridge regression and lasso regression in class. It's very similar, but uses a different penalty metric, something called L2. Coefficients only approach 0 in ridge regression. So in ridge regression, you're not going to actually remove variables altogether. So in the lasso regression, if we go up to our lasso set, Let's see if we can find our lasso. Here's our lasso. In the lasso case, you'll see some of these coefficients are actually zeros. They actually do get all the way to 0, which basically means CNN 6 and 7 we could throw out of our model. These are useless. 8 as well, and then 4 up here. Ridge regression will not actually get all the way to 0. So that's the primary distinction, but there's some more nuance to it. So we'll go ahead and do this ridge regression. All right, and so here we can see the ridge regression results. And these will be, again, slightly different. So we have very, very similar to linear regression and the ridge regression. The output is very similar for that one example case, slightly different, but very similar. And the actual coefficients are very similar. CNN1, we have negative 1.15. Here we have negative 1.152. 36.874, 36.865. So in this particular parameterization, ridge regression and linear regression are very similar in nature. Ridge regression does tend to be more resilient to overfitting than linear regression does. The next thing we're going to look at is a support vector regression. So support vector regression is really, really powerful when there's some level of error that you don't care about. Basically, what this is going to do is it's going to fit a best line. It's going to find the best coefficients for any given for your model, but it's going to ignore some amount of wiggle room on either side. This epsilon value you set essentially says, okay, ignore some of my error. Some of my error doesn't matter. If I'm wrong by 10%, I don't care. Those types of things are what SVR lets you do. So this is from sklearn.svm, which stands for support vector machines. We're going. And so what I'm doing here is I'm just setting a random state. The tolerance, don't worry about this too much. This is just how long we'll let the algorithm run before we tell it to stop, tell it it's good enough. And then we're going to do the same thing as before. All right, so these are the coefficients from the support vector regression. So in this particular case, you can see all of the different parameterizations. You can see, again, CNN10's still tending to be the biggest one. Similar to the linear regression and bridge regression, we do not have things approaching 0. So SVR does not necessarily penalize you for having too many variables. So this can also lead to an overfitting scenario. But again, it's very, very powerful in the cases where you kind of don't care about certain levels of error. The next thing we're going to talk about is a Huber regressor. So the Huber regressor, this is essentially regression that is strong when you have concerns about outliers in your data. So in some cases, you may have, just data, 1 or 2 data points that are extremely kind of far out there, and those data points can cause havoc on a lot of these other modeling classes. Support vector regression, ridge regression, linear models especially are extremely sensitive to kind of large outliers. So Huber regression, we'll talk a little bit more about how you overcome this, but essentially what it's doing is it's subsetting the data into 2 different groups: outlier data and not outlier data, inliers and outliers, and then it uses that split to weight each group. So you end up building a weighted model that's really good at predicting your inliers and kind of okay at predicting your outliers. All right, and there we go. So this is the Huber regression. Again, let's take a look at CNN10. Very large values. That means for the data that is kind of the inliers, the data sets that do not appear to be outliers, CNN10 is even stronger. We also see CNN11, right, starting to pop up in some of these models as well. The next thing we're going to look at is decision tree regressors. So decision tree regressors are going to be a little bit different than the other classes that we've looked at so far. So everything we've looked at so far has been predicated upon this idea that we're trying to solve this linear model that has some set of coefficients, and we're trying to predict what these coefficients should be. That y equals, beta 0 plus beta 1 plus beta 2, what should the betas actually be? What a decision tree regressor does is it identifies the best splits in your data that describe different groups that have different outcomes. So for example, what if every single time CNN10 was bigger than 40, just as a completely arbitrary example, there were always 200 people in front of the camera? That is the type of split that decision tree regressors help you identify. So in the case of a decision tree regressor, we're not going to have this list of coefficients. So just to illustrate that, let's go ahead and fit our model. In this case, there's not going to be anything that we can fit, right? The decision tree regressor has no attribute coefficient. There is no coefficient here. So we have to display the results from a decision tree slightly different than we do all of these other regressors. So I'm going to copy in a few different imports. You should be able to do this. You should be able to just copy and paste these. If not, you may need to do a conda install for example, IPython, but I don't believe you will have to. You'll remember we did the conda install at the very beginning of the first video for GraphViz, and this is why. What we're going to do is we're actually going to print out what the tree looks like. So I just copy and pasted this. Essentially what we're looking at here is we have the decision tree regressor. There's some information on the different models that we're going to be using. So in this case, we have the tree regressor. We have the feature names or the actual X column names. So that would be like CNN1, 10, so on and so forth. And this is just information on how to actually print it out. So I'm gonna go ahead and click run. And here we go. So this is the final output that we would actually get for a decision tree regressor. So again, we don't have these parameters. Rather, for row 996, right, the same row that we've been using for this example, the way that we're going to figure out what its prediction is we're going to follow the tree. So does row 996 have less than or equal to 0.651 for CNN10? If that's true, go this way. Does row 996 have less than or equal to 612 for CNN11? Let's say that that's false, so we're going to go this way. Is CNN3 less than or equal to negative 0.185? Let's say that's true. We're going to go this way. That means that we would estimate for row 996 a 171.12. So we just follow the tree for that particular variable. Now there's some important trade-offs here. This is very powerful when you have hard splits in your data, but you have to be careful about the max depth that you allow. So if we were to take this off, no more max depth, and I run the exact same model, we're going to get a very, very different tree, and it will take a little bit longer to fit, because what it will do is it will build a tree that has a lot of variation within it to try to get as accurate as possible of a result. So if we scroll down here, you can see, I mean, good Lord, I can't even get close to seeing the entire tree in this notebook. I mean, it is phenomenally large with all of the different splits that it will create. The deeper the tree is like this, the more nodes it has, the more prone it is to be overfitting, right? A tree like this with absolutely no limits on its depth is going to be dramatically overfit. The chance that you're going to get anything meaningful out of this is very low, because you're going to predict your own data really well, but you're never going to be able to apply it to any other data sets. So setting some form of a max depth parameter is highly advisable when you're using these regression trees. The next thing we're going to look at is a radius neighbors regressor. Essentially what these do is they create a kind of local estimates across your data set. So every unit of observation, you take all of its neighbors and then you fit a model with only that group of information. And you go and you repeat that over and over and over again for every single one of those cases. The easiest way to think about this would be geographic space. So if you think about it, you're going to fit a model for your neighborhood, literally where you live, and then the neighborhood that's the next neighborhood over, all of those households would be a part of that cluster, so on and so forth. You're building kind of different models for different groups that you believe would be similar. This is really, really powerful in cases like neighborhoods, like geographic neighborhoods, because there are lots of trends that are different across neighborhoods or across states, for example, within the United States, that this allows you to capture. If we actually go in and we try to print out the coefficients for this, we will get an error. And the reason we get an error here, every single one of our neighbors, or every single one of our units of observation has a different model. So let's take a quick look here at just our example. So this row 996. So what I just did was I copy and pasted this command, which what this does is it tells me for row 996, what are the things that we are considering neighbors? And when we say neighbors here, what we mean is neighbors in multidimensional space. Minutes that had similar CNN 11, 10, 3, 9, so on and so forth. That's how we're defining a neighbor. And this tells me, okay, minute 1079 looked a lot like 996. Minute 950 looked a lot like 996. 2500 looked a lot like 996. So these are the minutes that we're going to actually try to fit with. We can then do a prediction using that neighbors set. So the same predicts that we would normally do. And so we would get this, a 56.8 in this case. The next thing that we're going to do is look at an MLP regressor. So this is a multi-layer perceptron. This is essentially a neural net. There is a strong risk of overfitting if you don't have a lot of data. And just like the radius neighbors as well as the tree models, we will not have a set of coefficients. We aren't going to go into visualizing these neural nets and exactly how they work, but we will talk a lot more in class about the details. So from sklearn, okay, so we've gone ahead and we're going to do our prediction. Don't worry too much about these settings. Again, we're going to cover in class like exactly what these things mean. But this is the same as always, MLP. We're fitting our model and then we're going to use it for prediction. So we'll go ahead and run this. And this will take a little bit longer to fit than other modeling classes. And there we go. So now for this one example, we have a 33.29 for just that one case. Okay, so the next thing that we're going to talk about is a least angle regression. So a least angle regression is essentially a modeling paradigm where you're going to go in and add variables in one at a time, adding the remaining variable that is most correlated with y each time. And you're going to do that until you reach some sort of a threshold that the user sets that basically says, okay, if it's not at least this good, don't enter it into the model. This is really good for building, it's a kind of another approach to what lasso regression is trying to do, trying to find ways to, not have too many things that you're adding into your model. This is really a good approach for avoiding overfitting. So this is from sklearn. All right, so what we're doing here is we're going to say, okay, give us a least angle regression where we're going to be only taking the one best coefficient. So the number of non-zero coefficients that we're going to allow is going to be 1. So we'll go ahead and run this. And then let's take a look. This will give us coefficients. Here we go. And you can see the CNN10, again, is the one that it did. Basically, this was the best first coefficient that it found. If we run the estimate, we get 81.26 in this case. The next thing we're going to talk about is the elastic net. So elastic net is another way that we're trying to penalize models for including too many variables. It's essentially trying to combine lasso and ridge regression. It can remove variables, but it's less likely than it will compared to lasso. It's a good alternative if you need fewer variables, but lasso is underperforming because it's removing too many. It's kind of a middle ground between these two. So go ahead and run. And there we go. So this is the elastic net. Again, you can see all of the breakdown. You do see, importantly, some of these variables are at 0. So we are removing some of these variables from the model. And you will see also, kind of as we've seen a lot here, CNN10 is still receiving that highest overall coefficient value. The next model we're going to talk about is a passive-aggressive regressor. Essentially what these passive-aggressive regressors are doing, other than sounding cool, is they are iteratively building a model based on adding one row of data at a time. As each row of data is added, the accuracy of that specific row is calculated, and then a new model is fit that is constrained to be similar to the previous model, but changes a little bit to reduce the error of the most recent observation, that row that you just put in. The goal of this model is to ensure it changes as little as possible across rounds. So this is really, really good for online learning where you're getting lots of new data all the time. So if you are predicting something every minute and you want to let the model learn over time, but you don't want to change it too much. So we'll go ahead and do this one. And there we go. So you can see here, again, CNN10 is the biggest, but with this, with slightly different parameterizations. Similar to the linear models, these are the kind of traditional OLS. You are not removing variables in this case. So passive-aggressive regressors, these are not necessarily resilient to overfitting. The last model we're going to talk about is something called RANSAC. which stands for the Random Simple Consensus. So RANSAC is another type of model that is really good for outlier issues. So first thing RANSAC does is it defines every single row as either an outlier or an inlier, and then it randomly selects a subset of the inliers and fits a linear model using only those. So then you basically use only that random subset of your inliers, and you fit a ordinary regression. So the idea is to make you more resilient to outliers by throwing out the outlier data and then fitting kind of another type of regression. So in the default case, we're just going to be using a normal linear regressor, but you could use a RANSAC model in conjunction with, for example, an elastic net or a lasso regression. And there we go. So this is the RANSAC regression. So again, something that is resilient to outliers. All right, so in the next video, we're going to compare all of these different models, and we're going to talk a little bit about the different ways you can use to figure out kind of which model to pick.